Get started here, shall we? You now know how to find that. The what? Resultant vector. So if we have some amount of motion on one axis and some amount of motion on another, you know how to use Pythagoras to find the resultant. You know how to use trig to find that angle. You know how to do a heading. So you know how to do this algebraically and trigonometrically. Now here's a different question. If I tell you that you have traveled at some heading, maybe you've traveled 11.2 kilometers at 39 north of east. But what you actually want to know is how far north of a given point you are. The tools that we used yesterday won't get you that. So this is called solving a resultant vector. And what we're going to do is solve and resolve. So this is solving for the resultant vector. What we're going to do here is resolve a piece of motion into its two vector components. So this is called resolving. So if we want to know how far north and how far east we are, we have to use a different set of tools. So this is more trig. What we're going to do here is take that resultant vector and break it into the x component and the y component. This is where we use sine and cosine, because when we're given a resultant vector like this, we're given an angle and we're given the hypotenuse. The resultant is always the hypotenuse. So to break it into the components, what you have to remember is that you have a side opposite the angle and you have a side adjacent the angle. I draw those stupid little lines because I screw up if I don't. Not all the time, but enough that I very often draw my stupid little lines. Go ahead and do this one together and then we'll do the one in the book. So if I want to know what the delta y is, or the delta x, and this is my resultant, I have to remember that sine equals opposite over adjacent, cosine equals, geez Louise, that's tangent. So, get it? So, cosine equals adjacent. Sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse. So, my resultant is my hypotenuse. If I want to find we'll start with the x displacement. That's the component that is adjacent to the angle that I've been given. So I know I'm going to use cosine for that. And I would advise that starting out, you actually go the long way around the barn. You'll get really good at these to the point where you will not have to go the long way around the barn. But to start, what I typically look at is saying, well, this cosine of theta, and that's my theta right there, would equal my delta x over my resultant. Three-part algebra. Well, that means then that cosine theta times r would give me my delta x. So let's go ahead and solve for it. You got calculators, right? Okay, so you should get a raw answer of 8.704 on and on and on and on kilometers is the eastward displacement, and this would be to the east. And we need to specify direction because it's a vector quantity. So with sig figs, we've only got two sig figs. This would be 8.7 kilometers east is your x displacement. Let's do the y. So I know that my y displacement is opposite the angle that I'm describing. So I'm going to go ahead and write, I know I'm going to use sine. So the sine of theta is going to be equal to my opposite, delta y, over my resultant, which is my hypotenuse. So therefore, sine theta times r will give me my delta y. Okay, so I get a raw answer of 7.0483 on and on kilometers north is my delta y. When I sig fig that, I'm going to get 7.0 kilometers north equals delta y. Okay? Pretty straightforward. Now here's the cool part about resolving vectors. You can do this for any vector quantity. So we did it for displacement, which is a pretty easy way to start, because you can think in these terms. If you're walking in a city on a grid block pattern, you can think about it in terms of, you know, driving and imagining your place on a map. It's easy to visualize. What's a little bit more abstract, but becomes very useful in here, is that vector quantities like velocity and acceleration can also be resolved into their component pieces. Let's do the sample problem together, and then I'm going to cut you loose. So this is on page 93, and then I'm going to cut you loose to work on some homework. Okay, so this is nice because it gives us an example of using vector resolution to work with something that's not a displacement. So we're to find the component velocities of a helicopter traveling at 95 kilometers per hour at an angle of 35 degrees to the ground. The thing that they're going to start the discussion with, and I will too, is a coordinate system. So again, we typically use x-axis as the ground, y-axis is directly up, and we've drawn a nice little picture. I'll add my own little picture to it. There's my helicopter. And it's traveling at 35 degrees above the ground. Its overall velocity is 95 kilometers per hour. So what we do is visualize this as a triangle. We have our v sub x and our vy. Is it important to use the v sub x and the vy? Oh yeah, because starting later in this chapter, we're going to be doing a lot of work that requires you to differentiate between velocity on the x and velocity on the y. So I'm going to set up my trig functions. I know that sine theta is opposite over hypotenuse, and cosine theta is adjacent over hypotenuse. And I know that my vy is, my velocity on the y-axis is opposite the angle that's being described. So I know that sine theta will equal velocity on the y times overall velocity. So you can write just v for overall velocity. Sometimes we do that also, which is v resultant, which tells us that this is something that's made up of two components. So therefore, sine theta times resultant velocity is going to give us our y. So sine of 35 times 95 kilometers per hour gives us our velocity on the y-axis. I have a raw answer here, but my answer is not complete. What else do I need to add to this? I need to sig fig, obviously. What else do I need to do? It's a vector quantity. Direction. So in this case, we're not given north, south, east, or west. We can't artificially make that up. But what we can do is reference what information we're given. And what we're given is the ground. So here we would say, once we sig fig it, it's 54 kilometers per hour. What would be a good reference for that in terms of direction? This is on the y. Straight up. Straight up. You can say vertically, you can say straight up, perpendicular to the earth. Any of those work. So you just have to make sure that whatever descriptors you're using for that directional reference are clear. So straight up works, perpendicular to the earth works, on the vertical works, all those. So I'm just going to put up. Okay, so now I want to find the component of velocity that's on the x-axis. That's adjacent to the angle, so I'm going to use cosine. And I know that cosine of theta is equal to v sub x over v resultant. Cosine theta times v resultant equals v sub x. Cosine of 35 times 95 kilometers per hour will give us our v sub x. My raw answer for v sub x, 77.819, blah, 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 blah. What's a good directional tag to put on that? You could use lateral, you can use along the ground, you can use forward along the surface of the earth, you can use forward along the horizon or on the horizontal. Any of those work. You know, we know it's going forward. This is positive. So I'll probably default. So I typically use along the horizon or on the horizontal. Lateral is not wrong. Forward along the surface of the earth is not wrong. It has to be clear that anybody could look at it and tell what you're talking about. So where is the greater velocity, on the x or the y axis? It's on the x. It's actually moving faster on the x-axis than on the y-axis. We would expect that. Where would we expect the velocities to be evenly split? At what angle? .45. At 45 degrees, you would have equal components of your velocity on the x and the y-axis. Okay, all of the 3B problems, oh, I'm sorry, we didn't do the 3A problems. 3A and 3B, or did I assign the 3A problems yesterday? Oh, okay, I'm not losing my mind completely, only partially. So the 3B problems are assigned. So that's page 94, numbers 1 through 7, and I'll give you some time to work. I'll turn on your station.